Okay, let's do another example. Now, up to this point, we never talked about the magnetic field created by a single moving charge. We only had a charge carrying wire. Well, we know that the charges are moving in that wire and hence they create a magnetic field. But we never talk about the magnetic field of a single charge. Now let's study that problem. What will be the magnetic field created by a single charge? Let's suppose that we have this charge, Q. It is moving with a velocity v. And let us assume that we would like to calculate the magnetic field, let's say at this point, P. That's what we would like to calculate. Now, first of all, why will there be a magnetic field to start with? At that point. Electric field is changing. As our particle is moving, as this charge is moving, the electric field at this point will be changing. Now, for the time being, let's just assume that the electric field is always has this 1 over r squared form. It's always radial. It's all r hat over r squared form. It has the same form. So as this charge is moving, the electric field at this point will be changing constantly. And since the electric field at that point is changing constantly, there won't be any, there will be a time-dependent magnetic field. Now let's start with the, now if there's a time-changing electric field, we know that it will create a magnetic field, and we can calculate that magnetic field using this relation. Mu 0, epsilon 0, d phi e by dt. Now, at this instant, we can determine what the electric flux will be, but we will do it in a moment. First, let's look at the left-hand side. B dot dl. Okay, again, we need to evaluate this integral somehow. And to be able to evaluate this integral, we first need to determine the general properties of the magnetic field. So what do you think about the properties of the magnetic field? What will be the magnetic field lines look like? Well, they will form closed loops. Magnetic field lines always form closed loops. That is one thing we know. Now, the second thing we know, if we just rotate our system around this line, nothing should change. So these already tell us that the magnetic field lines at this point, magnetic field lines should just form closed loop around this axis. So this is how the magnetic field lines will look like. This will be the shape of the magnetic field lines. Again, let's assume that this is the direction of our loop. I will assume such a orientation. So if I look at it straight from here, that line goes counterclockwise. So that will be important in determining the sign of this flux. So if this is a positive charge, let's just assume it's a positive charge. And let's assume that this is the orientation of my loop. Is the electric flux positive or negative? It is positive. So for this orientation, phi e is positive. That is something we know. Now let's just write the magnetic field and the L vectors as this is the L tangent to that circle. The magnetic field line will be, again, it will depend on this rho, this distance from the axis. It will depend on that. It will also depend on this distance, let's call it d, or let's call it L. The magnetic field intensity can depend on both of them. It can depend on L, and it can depend on rho. And also, of course, time. But you see, it will depend on time through L. L will be changing in time. So that's what causes the time dependence of the magnetic field. So these we know. So we can just evaluate this integral. B dot dl is just 2 pi rho times B. Again, this rho is the radius of the circle. It's not the charge density, it's just this radius. Now comes kind of the hard part. What is the electric flux through this area? Well, we already know what the electric field is. So this is our system. The electric field, we already assumed that it was given by 1 over 4 pi epsilon 0 q r hat divided by r squared at this point, let's say. That is the distance r, this is the vector r hat on the edge. How should we proceed? Now, first of all, let's first choose a surface. What kind of surface should we calculate the flux? Which ring? Oh, so you mean, let's just take this circle. Okay, this is my ring. So here, this is the velocity of my object. It is just coming towards me. Now, one thing we can do is, of course, divide this into small rings. So we have all these small rings. We can just pick one of them randomly. Let's say this one, just any arbitrary one. So you're assuming that we assume this disk, flat disk. We divide this flat disk into very small rings. Eventually, we will assume that the width of each one of these rings goes to 0. Now, if we just take this one, the area of that ring is, if we say this distance from the central axis is just r, it is 2 pi r times dr. This is the area of my ring. Now, the flux that goes through that is electric field at that point times 2 pi r dr. You see, this is my charge, this is my ring. Now, just don't confuse the different rings. I have various rings now. There is the outer ring over here. I have calculated B dot dl for this outer ring. And now I need to calculate the total flux. Now, to calculate the total flux, first of all, I just decided to use this disk. I can choose any area that has this outer ring as its boundary. And I just decided to use this flat disk as my area. Since I'm using this flat disk as my area, I just divided this flat disk into very small segments, very small rings itself. I took one of those rings. I know the area of that ring is this one. I chose the one that has the radius small r and has a thickness dr, so its area is 2 pi r dr. The flux that goes through it will be E times 2 pi r dr. Now, I'm just considering this is my ring. This is my charged object. This is the path of that object. This is R. Now, this is the electric field. the electric field on this ring is pointing in this direction. Now remember, the flux is E times the area vector. So I have to multiply this thing by cosine of the angle. So the area vector, this is my ds. And this is my angle, let's say theta. So the flux is not just electric field times the area times cosine of this angle theta. Now, any questions on this one? Which one? This angle is also theta. Yes? Now, I just took this ring. Remember, in this picture, this is my ring. I'm looking at this ring, and the charged particle is coming like this. In the bottom picture, I just look at it from this side. So this ring just looks like a straight line from this angle, from this point of view. It's just a straight line, and the charged object is just arriving from the left. Now, this is equal to, now the magnitude of the electric field at this point is, let's say this is my, what did we call it, L? No, hold on. Okay, the L is the whole thing. Okay, this is L. Let us call this one large D. I don't want to use small d. Small d I'm using over here. So the magnitude of the electric field is 1 over 4 pi epsilon 0 q over d squared. Now I have 2 pi r dr, and then cosine of this angle is nothing but L over D. So this is equal to 1 over 4 pi epsilon 0 q. Okay. This is our system. We have this charged object moving its velocity v. We want to find the magnetic field at this point. We said that, okay, we consider such a loop. This distance is L, and this has radius distance rho, and so B dot dl, we said that this is 2 pi rho times B. And then we had to calculate the flux. We consider this is our disk. All of it has radius rho. So we just imagine the small part over here. We divided this into very small rings of radius r, and the flux, the area was 2 pi r dr, and the electric flux is E times 2 pi r dr cosine theta, where this angle theta was this one. This is my ring. This is my moving particle. This is the distance r. This is the charge q. So this is the direction of the electric field, but this is my ds, the area element, since I'm considering a flat disk. And this angle over here is theta, which is the same thing as this area over there. So this electric flux, if we just also substitute the magnitude of the electric field, is equal to 1 over 4 pi epsilon 0 q over, now this distance we just call d, q over d squared times 2 pi r dr. This distance was L, so cosine theta was also L over d squared. So let's do the cancellations. We have pi's cancel, L over d. So we have 1 over 2 epsilon 0 q L over LR over d cubed times dr. This is the flux that goes through one of these rings. Of course, we have to calculate the total flux. Now, the total flux will be just the integral of this one. Just the sum of the contributions of all these small rings. Now, the smallest ring has radius 0. The largest ring has radius rho. You see, if you go back to our original picture, we are trying to calculate the flux that goes through this area, through this disk, which has the radius rho. Now, this is not a complicated integral. Remember, d squared now d squared is nothing but L squared plus R squared. Or d is L squared plus R squared square root. So if you look at this R over d cubed term, this is R over L squared plus R squared to the 3/2. This term is nothing but d by dr of 1 over L squared plus R squared 1/2. If you take the derivative of this term, you get minus this one. So if you just put an additional minus sign over here. So this is our integrand. This is everything that depends on R over here. Q is independent of R. L is independent of R. The only thing that depends on R in the integral is d cubed. So everything else, everything other than this one, we can take out of the integral. So what remains inside is just the integral of a derivative. So phi e is equal to q over 2 epsilon 0 L minus d by dr. So the integral of minus d by dr, or let's even move the minus sign outside, of 1 over L squared plus R squared 1/2 is integral from 0 to rho. Yes? So the R's, you can think of it, say, okay, the R's will cancel, so I'm just summing the changes of this factor as R goes from 0 to rho, or you can say the integral of a derivative is nothing but the function itself. So this is our flux. Now this is the integral of a total derivative is easy. This is equal to minus q over 2 epsilon 0 L 1 over L squared plus R squared 1/2 from 0 to rho. This is phi e. And if you just place, this is R equals 0 to rho, so this is minus q over 2 epsilon 0 L 1 over L squared plus rho squared 1/2 minus 1 over L. This is our flux. Is it time dependent? It is time dependent. Remember, rho is independent of time, but L changes with time. So that's what will bring us the time dependence. What will create the magnetic field. Now also, if you look at these terms, this term and this term, they will just cancel each other. No, not cancel, I mean these L's will cancel. There's no time dependence. This is just a constant term over here. So that's also another thing. So when we take the derivative of the flux with respect to time, only this term will contribute. Let me just take this term. Now dl by dt. What can you say about dl by dt? V or minus V? Now, in this configuration, at this instant, it is minus V. Remember, the L is decreasing in time. Yes, L is decreasing. dl by dt is a negative number. So it's a minus V over here. So let's take this derivative. Now it's almost over. So this is equal to, first take the derivative with respect to L itself. Minus Q over 2 epsilon 0 times 1 over L squared plus rho squared 1/2 plus L times minus 1/2 twice L over L squared plus rho squared 1/2, 3/2 times minus V. Nope. Okay, so what did I do? I'm just taking the derivative of this term over here. Its derivative of L with respect to L is just 1, so it gives me this term. Plus I take L times the derivative of this term, it brings a minus 1/2 because it's minus 1/2 power. I get the derivative of the inside is just 2L divided by L squared plus rho squared. Just decrease the power by 1 times dl by dt. Here I just use the chain rule. I mean, this expression depends on time only through L. So I take the derivative with respect to L and multiply by the derivative of L with respect to t. This is equal to QV over 2 epsilon 0, 1 over L squared plus rho squared to the 3/2. Inside what I have, L squared plus rho squared minus L squared. I just equated the denominators. I just multiply this one by L squared plus rho squared, the numerator and denominator. That's why I get this term over here. This 2 cancels this 2. I have a minus L squared. So L squares will also cancel. L squares also cancel. And this is what we end up having. Rho squared over L squared plus rho squared to the power 3/2. Okay, so this is how the total flux going through my area changes as a function of time. Okay, so finally, the last point, we have to equate these two expressions. We already have this result, 2 pi r times b. Two pi r times b should be equal to mu 0 epsilon 0 d phi e by dt. This is mu 0 epsilon 0, all this expression. And now epsilon zeros, they also cancel. Sorry, this is not r, this is rho. That is how we had defined it. There's a mistake over there. Now this radius is rho. Okay, so rho's cancel. And we have b is equal to mu 0 over 4 pi q times v rho over L squared plus rho squared to the 3/2. Okay, this is our B, the magnetic field created by this moving charge. Is this time dependent? So there's a time-dependent magnetic field which will create an additional time-dependent electric field which we should add to our initial electric field, which then will be an additional time-dependent contribution to the electric field which will create an additional magnetic field, etc. So you have this infinite terms. But let's do one more. Let's look at this one a bit more carefully. Is it positive? is positive, B is positive. So the initial choice of our loop tells us what the direction of the magnetic field is. So if we have this point charge moving in this direction, then at this point, remember we chose our loop direction to be, if you just look at it from this direction, it's just counterclockwise. So this tells me that the magnetic field is also counterclockwise. And you can just use your right-hand rule again. If positive charge is moving like this, your thumb in the direction of the positive charge is just like the current. I mean, if the direction of the point charges tells you the direction of the current, then your other fingers shows you the direction of the magnetic field. Now, let's just do one more thing. At this point, the magnetic field is out of the screen. Okay, so, and let's see, this is, we had named this as R, yes, D. Okay, so this distance is L, this distance is rho. So B is equal to mu0 over 4 pi QV times the component of D perpendicular to rho, perpendicular to V. Let's call it D perp times 1. Now, let's do it right. Q times D perp V divided by D cube. Now, D perp is the component of D, if we just think of it as a vector, perpendicular to RV. It is nothing but rho. L squared plus rho squared is nothing but D squared to the third half, that gives me the D cubed. But this is nothing but mu0 over 4 pi Q D vector, yes, D vector cross V divided by D cubed in magnitude. Remember the definition of the cross product. If you have two vectors, the magnitude of the cross product is nothing but the perpendicular component of one of the vectors times the length of the other one. Here we have the perpendicular component of D multiplying the other vector V. So the magnitude of D cross V is nothing but rho times V. This is similar to the Biot-Savart law. What about the direction? Is D cross V, what is the direction of D cross V? In the opposite direction to the magnetic field. So V cross B is also has the same direction as the B. So if you just take mu0 over 4 pi Q V cross D divided by D cubed. Now the vector on the right hand side, we just proved that it has the same magnitude as the magnetic field. Now we also have V cross D also has the same direction as the magnetic field. So these two vectors are equal. Now this is an expression. How many of you had seen this expression before? This is not the Biot-Savart rule. Remember, the Biot-Savart rule just tells us the magnetic field of a current carrying wire. This is not even an exact result. The Biot-Savart rule is an exact result. It is valid for constant currents. This is not true. We have additional corrections to it. The exact magnetic field will be this one plus additional corrections. Now you see, this magnetic field is a time-dependent magnetic field, which will create a time-dependent electric field. And this new time-dependent electric field will create an additional magnetic field over here. Remember, we first started by assuming that our electric field was 1 over 4 pi epsilon 0 q over r squared, as if it was just a static charge. We assume that nothing changes there. And then we show that this electric field, since the particle is moving, it creates a time-dependent magnetic field. But this magnetic field itself creates a time-dependent electric field, an additional correction to our initial electric field. Now, the nice thing will be if you calculate the corrections to this one, the correction will be of this order of magnitude. They will be proportional to mu 0 epsilon 0 times the velocity. Now, assuming the velocity is constant, the object is moving at constant velocity, so this will be the corrections. Now, one question, what is the dimension of mu 0 epsilon 0? What is the unit? It is second squared per meter squared. How do you know that? What is the unit of mu 0? What's the unit of mu 0? Mu 0 is Tesla meters per ampere. Well, you can just use this one. P dot dl is mu 0 times I. The units have to match. Mu 0 has to have the units of B, which is Tesla, dl, which is meters, divided by I, which is amperes. What is Tesla? Now, what is epsilon 0? Remember, E dot ds is equal to Q over epsilon 0. So epsilon 0 should have the unit Coulomb per electric field unit. Electric field is newtons per Coulomb times meter squared. Okay, what's the unit of Tesla? Anyway, this way you can just continue and the result will be second squared per meter squared. It's just like 1 over some velocity squared. It has the same units. Do you know the values? Numerical values? Okay, just put in the numbers and you will see that it is 1 over the speed of light squared. It has the correct units. Numerically, they just turn out to be correct also. Now the question is, so if you look at this expression over here, this mu 0 epsilon 0 is nothing but 1 over c squared. So the corrections that you will get to this expression will be proportional to the velocities of the charge squared divided by the speed of light squared. So as long as your charge is not moving close to the speed of light, everything is fine. You can use this correction. The speed of light is something like, I mean, the fastest rocket we have just goes at a very small fraction of the speed of light. Well, for the time being, it's a coincidence, but in the next hour, we will show that it is not a coincidence. Not? Now, you see, if the v is not close to the speed of light, this term will be very small. Like if you are moving at the 1% the speed of light, which is huge, by the way. If you are moving at 1% the speed of light, this term is just nothing but 1 over 10,000. So the correction to this term, if you want to calculate the magnetic field of a moving charge, the correction to this term only will be just in the 4th digit. which you can just ignore for most practical applications. No, sure. If the particles are moving close to the speed of light, like in particle accelerators, this first term will not be enough to determine the magnetic field. Now you will derive the explicit expression for the electric and magnetic fields of a moving charge in third year or in graduate study. I will just show you the magnetic field lines. How do they look like? Now if you have a point charge Q, which is moving at a speed, let's say V, it is very close to the speed of light. Now the electric field lines, they are still radial. They will still be radial. I'm assuming that they are moving at constant speed. They will still be radial, but they will be concentrated only at the vertical direction. Electric field lines are not closed. They start from a point charge. So this is how the electric field lines will look like. Well, you see, if the electric field lines exist only in this region, the magnetic field lines will also only exist in that region. Because here, there's no electric field. The electric field will be very small. So the change in the electric field will be small. There won't be a significant magnetic field. So it just turns out to be the magnetic field lines are only in the vertical plane. Now, this is just, if you keep it in mind, it might help you in the future. But let's see, if this is the case, if this is not a coincidence that mu0 epsilon 0 is actually the speed of light, you see we determined epsilon 0, we know the value of epsilon 0 is the same in every reference frame. We know that mu0, the value of mu0 is the same in every reference frame. It's just a number, it's just a constant, it doesn't change from reference frame to reference frame because the laws that we wrote are valid in every reference frame. So these constants are also valid the same in every reference frame. But that tells me that if this product is actually the inverse square of the speed of light, it tells me that the speed of light should be the same in every reference frame. Okay, you can say that it's a prediction of Maxwell's theory, and it was also tested. And it was actually shown that the speed of light doesn't change from reference frame to the reference frame. But that is a serious problem for Galilean relativity for Newtonian physics. Because Galilean relativity tells us that the velocity of an object changes from reference frame to a reference frame. Now, that was one of the first approaches that people said that, okay, the Maxwell's law tells me that the speed of light should be related to this product. So then there was the question with respect to which reference frame. The first assumption was, okay, there's a preferred reference frame in which the Maxwell's laws are valid. That is called the rest frame of the ether. That was the first idea of a concept of the ether. There has to be some medium carrying these light. And this medium, in the rest frame of this medium, the speed of light is c. In every other frame, we have the Galilean relativity. But then there was this experiment of the Michelson and Morley. They tested whether the speed of light depends on the reference frame or not. And what they actually measured, that the change in the speed of light due to this change in the reference frame was negligible or zero. There was no dependence on the reference frame. They made quite a precise measurement. So now we know, experimentally we know, that the speed of light up to a very, very high precision is independent of which reference frame you measure it from. It is kind of funny. Let's say you are here shining a laser, I'm here shining a laser light. I measure the speed of light to be c. You start running in the same direction with the 99% the speed of light. And the speed of light that you measure is again c. Or you'll run, let's say, at the 99.9999% the speed of light, you will still measure the same speed of light as I did. You cannot. You cannot go at the speed of light. You can go very, very close to the speed of light. The photons will be just moving with respect to you at the speed of light. Okay, any last minute questions before we go for a break? It cannot. Okay, see you after the break.